There we go. Testing. 1, 2. Haha. Anyway. Shit, we're getting a bad reflection. Let's see. Let's try to. Stop. Stop. Damn. Is there a way to do this like at an angle maybe? If I turn it a little bit. No, that went the wrong way. Just so I can get the stupid reflection off the fucking thing. It's hard to like get people to read it. Take me out before you get you guys. Ah, God damn it. Jesus H. Christ. I still can't read a damn thing. I mean, getting a proper lighting set up, it's going to have to be like, just the light in here. I'll fix it. I'll fix it. It's fine. It's just working. The light on up there was reflecting. So, and this particular bass isn't very good either. I'm recording, by the way. Take me up before it gets here. I don't know the words. Oh man, what a setup. Yeah, good enough? Okay, I hope so. Let's give it a shot. No righty then. I hope I'm in the shot. Okay, I won't erase anything in case I need to do this again. Okay. Picking up from last time, we breezed through the whole thing high level. So I wanted to get into some details about the what's called the spin connection. It's a key element of the theory because it in our equations it's going to tell us how the curvature ultimately of the space that we're using produces interactions with particle states. So again, the theory that we're proposing here is a bit different from most theories dealing with Clifford algebras because we're proposing that the interactions are the result of a metric tensor inside of the space of the Clifford algebra. In this case, it's a 4 complex dimensional space. There are other ways to represent something similar. You get slightly different results, but we're going with this for now. And so that metric tensor expresses itself ultimately in our equations as a spin connection. So first I'm just going to walk through real quickly, and we'll make this a short video, talking about how we do this in spacetime algebra, which is the algebra of the Dirac equations. It manifests as the standard spin connection that you can read about online. It's on Wikipedia. They go through it. But I just want to present it here because this mechanism or this formalism is exactly what we're going to use, and I'll show you that after this, in the complex dimensional space. And you can see that there's some slightly different properties of the spin connection there, but that gives rise to the gluon fields as well as the electroweak fields or electromagnetism, W plus and minus and Z bosons. Okay? So, spin connection. Where does it come from? There's lots of ways to formulate this, but this is just a quick one so you can see. And I figured it would be smarter to just write all this out and as opposed to drawing it while we're going, trying to keep this shorter. You start with a metricity condition. So this is an equation that puts pinning down on what's possible for the geometry. We're saying that our generators in this curved space their covariant derivative is 0. So you can think of that as an extension or simple different version of this, where we're taking the metric tensor of our space and saying that its covariant derivative is 0. Now, in our complex dimensional space, it is conformally invariant, so you're going to see a slightly different equation there, but we'll get into that. In regular space-time, it's not conformal. So general relativity, covariant derivative of the metric is 0. That actually comes directly off of this condition because the metric tensor is the square of these Dirac generators. Okay. Again, we know that the curved generator is a linear combination of the non-curved versions through what's called a tetrad. And so taking the covariant derivative of our generator is the equivalent of taking the covariant derivative of this tetrad. And again, summation notation here is applied. So the real equation for this breaks down to the covariant derivative of the tetrad is 0. And we can write that out in the following format. You might say, well, what the heck is this? So here we have the derivative, the Christoffel symbol or affine connection from general relativity, and we have this additional term. In a sense, this additional term is defined by this equation. So what we're saying is, well, the covariant derivative of the tetrad is 0. This is a regular covariant derivative of a vector element, which we have here represented in mu. So I'm going to add an additional term on here whose job it is effectively to cancel out the rest of it. It's designed to give me 0. I don't know what it is, but I'm defining it this way. So using the properties here of how to reverse a tetrad, I can then solve for what this element is. So if you use this definition, then by definition, this is 0. That makes sense. It seems circular, but it's not. We just don't know what this is, and we're using this equation as a means to define it. Okay. It looks just like a variation of a Christoffel symbol, but against these new indices that I'm using capital Latin letters for to represent space-time in a Minkowski metric format. Okay. Again, the tetrad exists as a way to remove the curvature or remove the fanciness of the metric at a particular location. So it only is flat locally. It's not flat globally. That's important to know because what we're dealing with here is variations of Lorentz transformations as we move throughout the space. So this isn't fully generally covariant by its nature. You have to do that, you really need to be invariant in the Poincaré group, and that requires it to be invariant under translations, which are not representable in this way. If you want to read up on that, you can do that. In Clifford algebras, you just have to use either projective or conformally projective versions of Clifford algebra to include translations in the model. Basically, it becomes a rotation through the point n, with the point n infinity being the center of the rotation. I won't get into that. We'll stick with this for now. So now I have this term, and I have it by definition equaling this. And it's oftentimes we want to raise the index, so we can do that through this flat metric. This is the Minkowski metric. So multiplying it by here gives me one with them raised. So let's dig into this a little further because we really want to define further what this is. Is there another way to write it so that we can get a way of writing this? Switch that. Again, writing this out with the gamma A on the outside. There it is. So I've taken this equation here and I've included the gamma A part of this. And let's define a new object, omega alpha, as 1/8 this term, which we defined over here, the anti-symmetric representation of the gammas here. This is sometimes written as this. Okay, there's a 1/2. You get that? So this is the bivector version of this in the flat space. And what I want to do is calculate what this is relative to this object. Okay. So I'm skipping a lot of steps here, but I just wanted to give you a brief, and I can go into detail in a separate video on how to actually perform this full detailed calculating what this is. But breaking this out by its pieces and writing it all out, you end up having the bivector and then a gamma q minus gamma q and the bivector. So you can see that represented here with these different objects. We have to pull out the generators because remember the order of multiplication matters. And we can use this fact on how to reverse any two of the generators. It involves, in this case, the Minkowski metric. If these were more the generic versions, then it would be the generic metric. And what you find is that the second half equals this minus the first half, no, minus this whole part here. So these cancel, leaving you with this calculation here is 1/8 u for nu or eta rather and gamma, and all of this ends up reducing down once you're done converting and mixing the elements into this, which is exactly this term up here. So at the end of the day, the covariant derivative of the gamma matrices in the curved space can be written in the following format, where this omega is defined by this is defined by this equation, okay, being 0 ultimately. So what do we have here? All right, that's what we want to know. What do we have here? What we have is a representation of a covariant derivative now with the terms that allow us to write that in the local space, absorbing the curvature. So we're just using the standard gamma matrices from Minkowski space, which we all know and love from the Dirac's equation. So when we want to later then write Dirac's equation in a curved space, we can use this omega alpha here to represent that covariant derivative as in regards to gravity. We could do that because we've essentially absorbed gravitational curvature into here for the derivative, as well as into the tetrad on the outside of the derivative. Again, this works and is accurate when we say it's, when we only consider Lorentz transformation throughout the space. So this doesn't do with transformations I meant, like rotations basically. So that it makes the equation invariant under general rotations throughout the space for a general metric. But this is the prescription that we go through to derive what in the world this would be. Okay, so you imagine if we switch out of this Clifford algebra and go to a complex dimensional space, our generators are going to be different, but the process by which we determine what this is going to be very similar. So that's what we'll do next.